Good morning, everyone. My name is Shiva Chen. I'm a senior compiler engineer at ND's Technology. Today, my colleague Shankar and I will talk about compiler support for linkerization in RISC-V and the issues we encountered when polymerization in LLVM. The idea of linkerization in RISC-V is to reduce the number of instructions to access symbol. For example, function call can be generated by a single giant link instruction, which has signed 20V offset with PC-rated addressing mode. So you can jump to a symbol within positive or negative 1 MB. If the symbol is out of 1 MB range, compiler can generate AUIPC and jump and link the register pair. AUIPC can get upper 20V PC-rated address of the symbol. Jump and link register can get a low 12V address. So the pair can jump to the symbol within 32B PC-rated address. If the symbol and the code side are not in the same compile unit, compiler cannot know the symbol offset. To guarantee the function call can reach the symbol, the giant link and AUIPC and the giant link register pair will be generated. But linker knows the symbol address is the static linking. So linker can transfer the pair to single giant link if the offset can fit in the instruction. And that's what linkerizations do. To inform the linker which instructions could be transferred, relocation records have to preserve in the object file, which is the information required for relocation process. But what is relocation? It's a process the linker will fit in a symbol offset that the compiler cannot note. Linker will write the offset according to relocation records, which is stored in the relocation section of the object file. You can use the reop tool to see the content. The offset field in the relocation section point to the instruction need to be relocated, and there's a symbol field to indicate which symbol involves the relocation. And the relocation type, RISC-V call, tell the linker how to calculate the offset of AUIPC and the jump and link register. When the linkerization is disabled, linker will update the offset without changing the instruction. When the linkerization enabled, there will be an extra relocation type, RISC-V relax. It will point to the instruction could do the linkerization. In this case, RISC-V relax point to AUIPC with RISC-V call relocation type. So linker can know AUIPC and the jump and link register are the candidate and can relax to a single jump and link instruction. Jump and link is a PC-rated instruction. If the symbol is close enough to code side, it can transfer to a single instruction. So can we relax to an instruction which is not PC relative? For example, when you want to load a global symbol, we need a LUI to get high path address and a load to get low path address and load the content. And there's no PC-rated load in RISC-V. In this case, we can relax to a single load with GP-based register. GP is a preserved register. Compiler will not use it in register allocation. So it can assign GP a value and relax the instructions to GP base if the offset could fit in the instruction. To do the linkerization, linker has to know the GP value. But how does the linker know the GP value? GP will be assigned to the value of global pointer symbol in the linker script. So linker can know the GP value while linkerization. Linker script file describes the section layout. It can also be used to assign symbol value. You can generate default linker script by RISC-V LD with verbose flag. Global pointer symbol will be assigned to the start address of small data section plus hex 800. The matching number is the offset limitation of signed 12 bit. The immediate field of load store and the add immediate instructions are signed 12 bit. So single GP-based instructions with signed 12 bit offset should be able to access most of the small data section, which means if the data put in the small data section, it has great possibility relaxed to GP-based instruction. In RISC-V, any data equal or smaller than 8 bytes will put in the small data section. But if you compare with PIC or RBCC4 with large code model, there will be no small data sessions by default, because linkerization not support for PIC or RBCC4 with large code model. You can also use the compile flag small data limit to assign a custom small data limitation instead of 8 byte. There are GP initial instructions in RISC-V new lib CRT0, which will assign global pointer symbol to GP register. The initialization have to guard with no relax directive to disable relaxation. Otherwise, it will relax to GP move to GP instead of assigning symbol value to GP register. The table lists all the instruction patterns of RISC-V linkerization. Middle columns are the candidates. Right column are the result after relaxation. If the target supports C extension, the patterns can relax to C extension instruction. Compiler default will generate postal instructions for the patterns contain AUIPC because AUIPC has much complicated assembly form. Left column are the postal form of the candidates. Generally, the patterns are a function call, get symbol address, and load store symbol value. And the last pattern related to TP is for 3 local storage. LLVM upstream not support 3 local storage yet, but there are patches from Louis revealed are under review. In the next few minutes, I will address the issues we encountered when pluralization in LLVM. The issues are branch offset changed by relaxation. LLVM assembler always transfers C extension branches to 32-bit form. Label difference changed by relaxation. Alignment broke by relaxation, and the debug information become incorrect due to relaxations. About the first issue, the offset of local symbol will be calculated and written to the offset field before linking. In this case, branch equal to 0 has PC rated offset 8. So value A will write into the offset field of the branch. When the relaxation enabled, Louis and low will relax to single low. So the real offset becomes to 4, and the branch will jump to the wrong position. To fix the issue, we have to preserve the relocation type RISC-V branch. So the linker can recalculate offset. To preserve relocation type, we have to define the target hood should force the relocation in RISC-V LLVM backend, which will indicate the relocation type should leave or not. The function will return true when the relaxation enabled, so relocation type will be preserved. The next issue is related to C extension. To make sure the offset could fit in instructions, LLVM assembler may transfer C extension branches to 32-bit form. When we force to leave relocation type for relaxation, LLVM will assume all branch targets are unknown and always transfer C extension branches to 32-bit form. To fix the issue, we add a variable with force in the transformation function. To indicate the relocation type are forced to leave for relaxation, and the transformation will depend on the branch offset to fix the issue. And the next issue is label difference changed by relaxation. LLVM don't expect the code size will shrink after linking, so label difference will be calculated as a constant before linking. In this case, the difference of label 0 and the label 1 may change because the instruction between the labels may relax by the linker. To fix the difference, we have to preserve the relocation type RISC-V add 32 and the RISC-V sub 32. The suffix of the relocation types indicate the data width of the difference. There are 2 relocation types because each relocation type will attach with 1 symbol. By accumulating the result from RISC-V add 32 and the RISC-V sub 32, linker can get a new label difference. And the next issue is alignment broke by relaxations because the instruction before the alignment directly may relax by the linker. For example, if the add instruction already at the alignment position, when the relaxation enabled, Louis and the low will relax to single low. So the add instruction will move out 4 bytes and lost alignment. To fix the issue, extra null operations will be inserted, and the relocation type RISC-V align will be omitted. It will point to the first extra null operations and also indicate the number of null operations have been inserted. So linker can satisfy alignment by removing null operations. In this case, linker can remove null operations and preserve one null up to satisfy alignment of add instruction. And there are other issues related to debug information. My colleague Kai will share his experiences. Please welcome Kai.
Hello, everybody. I'm Kai from NDIS Technology. I know that my name is hard to pronounce it, so you could call me Kai for short. Today, I will share my experience on development of relaxation in LLVM, especially on debug information support. First of all, let me give you an example to show what is the problem in debugging when relaxation is enabled. If we have a simple program, it's just calling a printf to print something out. After compiling and linking, we know that AYPC and JLR will be shortened to JL if relaxation is enabled. So all locations of the instructions after JL are changed after relaxation. If we dump the debug line information through dropdown, we could find that line 7 is located at 10214. However, it's an illegal address in the program. The legal one is 10212 and 10216. When debugging, if user set a breakpoint on line 7, debugger will look up where is the line 7, and it will get 10214 according to debug line information. When user trigger the debugger to run the program, it will execute an immediate instruction at 10216. Why? Because debugger will insert a breakpoint at 10214. Unfortunately, the breakpoint will overwrite part of ADDI and part of LW. So instruction will be embedded instruction. The debugger shows it received a signal, segmentation fault. The signal will abort the debugging. It is catastrophe to have embedded address in debug line information. So why is there an embedded address in debug line information, and how to fix it? Before we dig into the problem, we need to know the evaluation interfaces in MCExpr. It's helpful to know the differences between these interfaces before handling the problem. In MC layer, all expressions will be expressed in MCExpr. For example, if we want to know the offset between two symbols, LLVM will use MCExpr object with minus operator to express the symbol difference. As the slide shows, there are many fault evaluation interfaces. The red ones will be affected by relaxation, and the blue ones will evaluate the expression to values regardless the relaxation is enabled or not. All these four functions will be implemented based on the green one, evaluate as relocatable IMPL. In this protective function, it will check the flag inset. If the inset flag is true, it will evaluate the expression to value directly. If the inset flag is false, it will check relax flag in advance to determine to generate fix-up to deal with it later or to evaluate the expression to values. After knowing the differences between these evaluation interfaces, we come back to see how to encode the debug information after compiling. In general, in drop format, LLVM will use tags and attributes to encode debug information. For example, if we want to know the address range of a function body, there will be two attributes, DWAT low PC and DWAT high PC under the subprogram tag. DWAT low PC is used to denote the start address of the address range. DWAT high PC is used to denote the length of the address range. So it will be a minus expression between last byte and the first byte in the function body. LLVM will use evaluate as absolute and set instead to false to evaluate this minus expression. As we know, this interface will generate fix-ups if relaxation is enabled. So the expression will convert to fix-up, and the fix-up will be converted to relocation when final layout. So linkers will know how to handle the value according to relocation types. So in general, debug information is correct in executable. Why is debug line information wrong? We found that there are two parts in debug information which are wrong after relaxation. One is debug line information and another is debug frame information. Debug line information is used to describe the relationship between lines and addresses. Debug frame information is used to describe the location of variable related to frame-based address. This slide shows how debug line and debug frame information are encoded after compiling. Debug line information will be encoded using LLC directives. A scanning instruction from top to down. LLVM will process the line information of every instruction. Debug frame information will be encoded using CFI directives. LLVM will calculate the address difference between two CFI directives. So all this information are not encoded as binary expression directly. It needs several steps to convert this information to final encoding. This slide shows more detailed description about how debug line information is converted from debug location to final layout. In drop debug case, there is a hook called begin instruction, which will be called before processing every instruction. In this function, it will check the line information of every instruction. If it is a new line, it will generate a symbol and create the mapping between the symbol and the line. The mapping between symbol and the line is called MC drop line entry. After collecting all these mappings, LLVM will use evaluate as absolute and set instead to false to evaluate the symbol difference in the mappings. If the expression could not be resolved, LLVM will create a fragment for the expression. A fragment is a reserved space for the expression value. When final layout, LLVM will use evaluate non-absolute to evaluate the expression in the fragment. As we know, evaluate non-absolute will evaluate the expression to values regardless relaxation is enabled or not. So LLVM assumes the value must be known when layout. So it writes the value into the object file directly. Linker has no chance to update the value after linking. That's why there is an embedded address in debug line information. The correct way is to, when handling the debug line fragment, it needs to generate fix-up for the fragment. In addition, LLVM uses ULEB 128 encoding to encode the address difference for debug line information. In order to handle it more easily, we use fixed length encoding for it. Similarly, this slide shows how debug frame information is converted from CFI instructions to final encoding. It has similar problems. So the correct way is to generate fix-ups when handling debug frame fragment. In addition, there are possibilities to encode 6-bit offset in debug frame information. So we need to add new fix-up types and the relocation types for 6-bit offset. That's all I want to share with you. Thank you.